Hello class. Today we're going to be looking at section 3.2, which has to do with applications of radian measure. Radian measure was a way of measuring angles in circles, which we discussed last time. If you recall, if you look at a circle of radius r and start at any point on that circle and travel a distance along it exactly equal to the radius r, then the central angle that is formed by that rotation is exactly 1 radian. Now you can go another radius's worth of distance and you end up with an angle whose measure would be 2 radians, etc. So what we would like to do this time is take a look at a circle of radius r again and look at an angle, not necessarily just 1 radian, but some unknown amount, say theta radians. Now, when you have a circle like this, then this central angle intercepts 2 geometric figures corresponding to that circle. One is this natural arc that you can see right here, and one is this sector that I'm coloring in blue. So the two quantities of interest are, one, the length of that arc, which we usually denote with lowercase s, and 2, the area of that sector. Now, using two simple proportions, we can come up with nice formulas for that arc length and that area. So first we'll start with the arc length. Notice that the ratio of that central angle theta to the angle which would correspond to an entire circle, which as you know is 2 pi radians, is the same as the ratio of the length of that arc to the length of the entire circle, which as you know is called the circumference, and its measure is 2 pi r. Now if we do a simple cross multiplication here for this proportion, we get 2 pi s is equal to 2 pi r theta. So this times this equals this times that. Now, if we solve this simple equation for s by dividing both sides by 2 pi, notice that we get quite a bit of cancellation. The 2's cancel here, the pi's cancel, and they do the same on the right side. And then we end up with s equals r theta. So there is the formula for arc length. That arc right there. All right. So we can set up another proportion that will help us find the formula for the area of the sector in here as well, which we shaded in blue. Notice that the ratio of the same angle theta to, once again, the measure of the entire circle, which as you know is 2 pi radians, is also the same as the ratio of the area of that sector to the area of the entire circle, which as you know is just pi r squared for a circle of radius r. Now if we go ahead and cross multiply once again, we end up with 2 pi a equals, now we're going to multiply those two, we get pi r squared theta. Now, if we solve this simple equation for a this time by once again dividing both sides by 2 pi, we notice that here the 2's cancel out as well as the pi's, but on the right side only the pi's cancel out. So we end up with a equals 1/2 r squared theta. And that right there is the formula for the area of this sector. So on the left side, we derived the formula for arc length, and on the right side here, we derived the area for the area of this sector. Okay, let's take a look at an example of how we can apply those two formulas. Let's suppose we have a let's say we have a circle of radius 10 feet and a central angle theta which measures 3 pi over 4 radians. And let's go ahead and find both the length of the arc that's intercepted by that central angle as well as the area of the sector that is intercepted by that central angle. So if we want to take a quick look at what that looks like, of course we can go ahead and draw a circle with radius 10 feet and the angle 3 pi over 4, as you know, if I were to put these dashed lines to help me out. So we have 1 pi over 4, 2 pi over 4, which is the same as pi over 2, 3 pi over 4 falls right here. So the central angle looks something like that. These drawings don't have to be 100% perfect, but they're very helpful. So this angle measures 3 pi over 4 radians, and what we're looking for in the first part is we're looking for the length of this arc. Okay, now if we use the formula, we always start by just writing the formula. Don't just start plugging in because that can get you in trouble. So we get S equals R theta, okay? And that's a formula you need to memorize. We always encourage you to understand rather than merely memorize in mathematics, but there are some fundamental laws and formulas, etc., that do need to be memorized. So these two are good examples of such formulas that need to be memorized. So now we're just going to simply plug in, and we end up with S equals, for R we have 10 feet, and for theta we have 3 pi over 4. Notice that the way we derived the two formulas indicated that we used radian measures. So anytime we want to use these two formulas, we need to make sure that the angle is given in radian measure. If it's not, we can still find the arc length and the area, but we would have to do a conversion from degree measure to radian measure so that it works out correctly. So now we're going to proceed, and notice here we can do some cross canceling. The 10 and the 4 leave us 5 on the top, 2 on the bottom. So we end up with 15 pi over 2 feet. Now, as far as finding the arc length, you're finished, and this is an actual exact answer because there has been no rounding involved. So this is what we consider to be the exact value of the arc length. While that's beautiful from a mathematical point of view, from a practical point of view, in most applications, you would want to get some approximate value for that. So if we go ahead and calculate that, so 15 pi over 2, so we'll just go to a calculator such as Desmos, and we'll type 15. In Desmos, if you just write pi, it turns it into a pi for you, and then we're going to divide by 2. And we end up, so let's say we want to round to 2 decimal places, so we get approximately 23.56 feet. So approximately 23.56 feet. So I'm kind of new with this tablet situation. I'm hoping my handwriting is going to improve. So hang in there with me while I improve. All right, so there is the exact value of the arc length, 15 pi over 2, and here's an approximate value rounded to 2 decimal places, 23.56 feet. So this one is approximate. All right, so we can do a similar analysis for the area. Notice that we start with the formula for the area, which is 1/2 r squared theta, if you recall, and we go ahead and substitute now. So we get equals 1/2. Now remember that the radius is 10 feet, so times 10 feet squared times theta, which after we make sure it's in radian measure, we can go ahead and just substitute 3 pi over 4. Okay, so now we end up with 100 times 3 pi over 2 times 4. And notice the feet are being squared, so square feet, which makes sense because the unit for area should always be square. And you should always make sure that you check your units to make sure that they make sense, because that also helps make sure that you didn't make some error in some step. Now we're going to go ahead and cross cancel the 4 and the 100. We know that that leaves us 25 on the top and 1 down here. So we end up with 75 pi over 2 square feet for the area. Once again, that's the exact value of the area. Why? Because we did no rounding. We can also, again, for practical purposes, go ahead and get a approximate value. So this time we're going to calculate 75 pi over 2. So we just type in 75 pi over 2. And we end up with 117.81 approximately. So approximately 117.81 square feet. This one is the approximate value, rounded to 2 decimal places. Okay, so let's go ahead and take a look at another example. And this time we'll look at a circle with radius 5 meters and a central angle measuring 100 degrees. Once again, we're going to find both the length of the arc that is intercepted by that central angle, as well as the area of the sector that is intercepted by that central angle. So if we do a quick visual, we have a circle of radius 5 meters and a central angle measuring 100 degrees this time. We know if we go straight up, that's 90, so slightly more than that. So that looks about an angle which is 100 degrees. So first we'll find the arc length as we did in the previous example, and I think you should be able to do this on your own. So at any point when we're going through this lesson, when you feel like there is a problem that you can go ahead and finish on your own, you should definitely pause the video, go try to finish it on your own, and then come back to see the rest of the work. That will be your best bet as far as learning is concerned. Okay, so go ahead and pause if you can and come back. Welcome back in case you paused. All right, so, and try to pause next time in case you didn't. All right, so we have S, we start with our formula, equals R theta for the arc length, and we're gonna go ahead and substitute 5 meters for the radius, and the angle we have to be careful with this time because it's given in degrees. So we can either do some side work and convert that into radians and then bring it in, or we can just bring it in right away and just take care of the conversion right here. So remember, if you want to go from degrees to radians, there's a unit factor we can multiply by, and the unit factor for conversion in either direction is either pi over 180 degrees or 180 degrees over pi if you're going the other way. In this case, we want the degrees down here, so the 180 degrees will go here and the pi will go on the top. Okay, so now if we go ahead and do as much cross canceling as possible, we should get, for example, we know 20 goes into both of these 5 times on the top, 9 times on the bottom, and that should probably do it. So we end up with 25 pi over 9, and don't forget the units, meters. Now, if we leave it as is, that's going to be the exact value of the, this thing is trying to bother me here a little bit. Here we go. So if we leave it like that, that will be the exact value of the arc length, meaning the length of this arc right here, which we're just painting in red. Or if we go ahead and plug it into a calculator, we can get an approximate value. So let's do that. 25 pi over 9. So let me just do a little bit of time saving here. So that's going to be 25 pi, and we're going to change the denominator to 9. And we get approximately 8.73. So approximately 8.73 meters. Let's make sure of that. Yeah, that seems to be right. Okay. Now, so there is the exact value and there is the approximate value for the arc length. Okay, so if we want to find the area now, we're going to start by writing the formula first, always, without plugging anything in. It's a very good practice to get used to. So we get 1/2 r squared theta. That's the formula for the area of the sector, which I will shade in blue now. The area of that sector. All right, so we're going to get A equals 1/2. For R, we're going to plug in the 5 meters and square it. And for theta, we're going to put 100 degrees and immediately convert that to radians, because that's the only kind of angular measurement that can be used in either one of those two formulas. So we're going to go ahead and once again multiply by pi over 180 degrees. All right. So, oops, let's come back. All right, so we end up with 25 times 100 pi over 2 times 180. We can go ahead and leave the degrees out because they cancel out. So now once again we know that 20 goes into 105 times and it goes into 180 9 times, and that should be all that we can do here. So, and the final units are going to be square meters. All right, so let's keep going. So notice 25, there's no more cross canceling possible, so we go ahead and multiply across. So 25 times 5 gives us 125 pi over 18 square meters, and that would be your exact area. And now we'll go ahead and get an approximate area as well. So we'll go back to our calculator and we'll calculate 125 pi over 18. Let me just start from scratch. So 125 pi over 18. And we get approximately 21.82 if we go to the 2 decimal places. So 21.82 square meters. And there is an example of the situation where the angle measure is given to you in degrees and a conversion is necessary. Go ahead and take a look at that. Make sure you absorb the material. Okay, let's take a look at another example that you can see on the left of the screen, example 2. It talks about latitude, which gives the measure of a central angle with vertex at Earth's center, whose initial side goes through the equator and whose terminal side goes through the given location. Reno, Nevada is approximately due north of Los Angeles. The latitude of Reno is 40 degrees north, and that of Los Angeles is 34 degrees north, which of course means north of the equator. And they give you the radius of the Earth, which is 6,400 kilometers, and we want to find the north-south distance between the two cities. Now, just a quick look at latitude in this beautiful image, courtesy of Britannica, Encyclopedia Britannica. Notice that you can see the latitude right in here. So from the center of the Earth, if you connect a line to the equator, you can measure this angle that the terminal side would make, because this terminal side is connected to the city of interest, and that is latitude. Now longitude also, while we're at it and we have the picture in front of us, is measured from this great circle that you see. It's the other great circle of interest on Earth, and a great circle is just any circle you can draw around the Earth whose center is the same as the center of the Earth. So this one is what we call the prime meridian, this great circle, and that one goes through Greenwich Village in the UK. And why was that chosen as the standard? Well, because the UK pretty much ruled the world at the time, so that's honestly why it is. And we've just stuck with it because it works. So that's why when you want to give the location of any point on the sphere, you can give the latitude and longitude, and that will pinpoint exactly one point on the sphere. So that was just to show you what we're talking about here. So now let's go ahead and take a look at the problem. Notice we can just go ahead and worry about the latitude at this time. So let's say that this is that segment side of the angle which is drawn to the equator, and we can go 34 degrees north, imagining the Earth is rotated so that Los Angeles and Reno happen to be on your right side when you look at the Earth. And so if we just label this as Los Angeles, and that's 34 degrees north of the equator, and Reno is at 40 degrees north of the equator, so not much more, but slightly more. So that is Reno. And notice this angle here that makes with the equator is 40 degrees. So of course the angle between them and the arc of interest, which we're trying to measure, this arc will correspond to that central angle in the middle, which is basically 40 minus 34, so clearly 6 degrees. Okay, so all those words, not to be scary, all they're asking you to do is to find the length of this arc, which corresponds to a central angle measuring 6 degrees, and the radius of the sphere. Let me go ahead and erase this so I can write that. The radius of the sphere is 6,400 kilometers. So it's just an arc length problem, basically. So we get S equals R theta. You know the drill, so you should go ahead and pause at this point, try to figure out the rest on your own, then come back to the video. All right, and welcome back. So we know the radius of the Earth is given at 6,400 kilometers, and this problem is in the PowerPoint that accompanies this lesson. And we're going to go ahead and multiply that by theta, which is 6 degrees, and as you know, needs immediate conversion because when you use theta in this formula, it needs to be in radian mode. So we need to go ahead and multiply it by pi over 180 degrees. So if you want to give an exact value for the arc length, then you should multiply everything out, but not the pi. Leave that as is in the form of pi. So we're going to go to the calculator screen. We're going to multiply 6,400 by 6 and divide it by 180. So 6,400 times 6 divided by 100. Okay, let's make sure that we got those numbers correctly. 6,400 times 6 divided by 180 is what I meant. Okay, so let's fix that. So 180, and we get 213.33, or basically 3 bar, right? That's a repeating decimal, so we know it's a rational number. So we can write 213.3 bar, and remember that calculation didn't include pi, so we need to multiply that by pi, and we know that that's going to be in kilometers. That is if you don't mind the answer having a decimal in it. Now, if you do, or if the, for example, problem in my MATLAB requires you to give a exact fractional answer, that's not going to be that hard either. This time, I think I'll go to the TI because it lends itself better to this kind of calculation. So if I just go to a TI and I type in $6,400 times 6 divided by 180, we get, okay, we typed 64. Let's go correct that. I typed 640. Okay, so let me redo that. So we have 6,400 times 6 divided by 180, and of course we get the same answer. However, there's a nice feature on this calculator which lets me turn that back into a fraction, and also in simplest form. So if I just hit math and then choose the first option which says convert to fraction, and when I do that, I get this nice simplified form. Now, if this were an algebra class, we'd be going through all that, but then we wouldn't have a whole lot of time for trig. So you should know how to do that. 640 over 3. So 640 pi over 3 kilometers is the north-south distance between Los Angeles and Reno. But of course, once again, unless you want to sound kind of nerdy, you don't want to tell someone the distance between two cities is 640 pi over 3 kilometers, right? So we usually will want to get an approximate answer, which we will now get by going ahead and multiplying out the pi. So if we just multiply that by pi, we get approximately, let's say this time, since it's a distance, let's go ahead and round it to the nearest whole number. So we get approximately 670 kilometers. All right, so go ahead and make sure that you understand that while I get this prepped for our next problem. Okay, next, let's go ahead and take a look at this other good example. It's example number 4 on the left of your screen. So basically we have two gears that are adjusted so that the smaller gear is driving the larger one. And the smaller gear is going to rotate through an angle of 225 degrees. And what we're asked is how many degrees will that correspond to on the larger gear. Now, they give us the radii as well. The smaller gear has a radius of 2.5 centimeters and the larger one has a radius of 4.8 centimeters. So let's go ahead and do a rough sketch of the situation here. So that one actually came out kind of oval. This program does a nice recognition of shapes, but sometimes it's my fault. Okay, so let's say you have the smaller one and you have the larger circle like that. Now, it didn't recognize that one as a circle, so it doesn't matter. Let me try one more time and then we'll give up if it doesn't work. So let's see. All right, it caught it this time. Now, so we have the smaller gear, which has a radius of 2.5 centimeters, and the larger one, which has a radius of 4.8 centimeters. Now, we know that the smaller gear is going to rotate a total of 225 degrees, which is 45 degrees shy of 3/4 of a circle. Let's say it's rotating this way, right? So if suppose you have a red dot right there, and as this rotates around for 225 degrees, a certain arc is going to be spanned, correct? So basically not quite 3/4 of a circle. So if this is half, about that much, right? So notice that if there's a blue dot that's traveling on the larger circle, as it does so, this is going to basically have the exact same length of arc traveled on it. So the blue dot will travel the exact same distance as the red dot did on the smaller circle. So basically what we're going to do is we're going to find out what central angle that distance will correspond to on the larger circle. So this is what we're going to calculate. So the first thing we're going to do is actually find out what that length is, which is going to be the same whether a red dot is traveling on the small gear or a blue dot traveling on the large gear. So let's go ahead and calculate that. So let me go ahead and do that in red. So we know that S equals R theta, and here we have r equals 2.5 centimeters. And we know that the angle of rotation is 225 degrees. Now, if we go ahead and immediately convert that to degrees, to radians, it's in degrees. We multiply it by pi over 180 degrees. So because we're going to be using whatever result this is again in the next part of the problem, we're going to try to keep this as an exact value. So we're going to go ahead and multiply it out, but we won't multiply out the pi. So we'll leave that as pi. So we're going to multiply 2.5 by 225, and then we're going to divide that result by 180, and we get exactly 3.125. Make sure. And that's going to be multiplied by pi. And the unit is, of course, in centimeters. So now we know the length of the distances traveled by the blue dot and the red dot. They're the same distance. So logic tells us that since this has a larger radius, it should be able to span that arc in less degrees than the smaller gear. So as common sense would dictate, we want to make sure that when we go through and we find the answer, that it is less than 225 degrees. If it turns out to be more, then we know that something went wrong. We must have made a mistake. You always want to have common sense activated as you go through steps. You don't want to just blindly do problems. All right, so now let's go ahead and work with the larger circle now. So we know that S equals r theta for that circle as well, for that gear, which is circular in shape. But this time we know what S is because it's going to be the same S. So 3.125 pi equals, we know the radius of the large gear is 4.8 times theta. So now we go ahead and solve this equation for theta, and we get theta equals 3.125 pi over 4.8. Now, if you look back at the problem, you'll notice it says through how many degrees will the larger gear rotate. And as you know, when we use this formula, the answer that we obtain is in radian measure. So if we want to get to the actual answer to the question that they ask, we should go ahead and now convert this to degrees. And you know that we have to use the reciprocal of the unit factor we've been using so far. This time we want the degrees on the top and we want the pi on the bottom. Now, if you notice here, the pi's are going to cancel out. So basically what we're going to type into the calculator is we're going to type in 3.125 times 180 degrees. Well, we don't need to write the degrees in here in the calculator. We just go ahead and go divided by 4.8, and we get approximately, to the nearest degree, 117 degrees. Now, let's see if that makes common sense, because it took the smaller gear 225 degrees to travel that distance, right? For a red dot on that gear to travel that distance. So as you can see, for the blue dot on the larger circle, it will take quite a bit fewer degrees to accomplish the same task. So that's basically how you go about doing a problem like that. You just have to relax your mind, look at the situation, and determine a game plan that's going to get you to the answer. So basically, with all word problems, the general strategy is 1, understand. Now, that is easier said than done, but what it entails is the most important step of all, because sometimes you can read a word problem one time and know exactly what they're asking for. Sometimes you may have to read it a few times. Now, in this understanding phase of solving word problems, you want to use diagrams, tables, whatever the situation demands, till you find out two things: exactly what is given and what is wanted from you. You have to be very clear about those two things before you proceed. From there, you're ready to go ahead and translate. So when we mean translate, we don't mean from French to English or anything like that. The translation here is going to be, well, at least in our class, from English to mathematics. So that's where you basically form the necessary equations. And the last step is actually the easiest. You go ahead and solve. So those are the 3 steps involved in solving word problems, whether it's in algebra or trigonometry or in any branch of mathematics. So make sure you absorb that. So if you need to back up and take a look at it, the way that you make sure you've mastered something basically is you want to make sure that you can read that problem, have a blank piece of paper in front of you, and work through it completely on your own without needing any help. At that point, you should be in pretty good shape to proceed. So make sure you do that before you come back to continue. Okay, let's go ahead and wrap up this section by taking a look at one last problem. It's a word problem, but it's a very simple one. Notice that example 5 on the left of your screen, you have a center pivot irrigation system which provides water to a sector-shaped field with the measures shown in the figure. So the angle of rotation is 15 degrees, and the radius of rotation is 321 meters. And basically what we're asked to do is to find the area of that sector. So basically all we are dealing with here is a circle with a radius of 321 meters and a central angle measuring 15 degrees. You definitely should be able to handle that at this point, so I recommend that you pause the video and see if you can get the answer on your own. Let's hide the work so you don't get temptations. All right. So I'm assuming you're back from a break. So remember, this time you're finding the area of a sector, so that's the formula you need to write down first. So the area of a sector, as you recall, is 1/2 r squared theta. R is the radius of the circle and theta is the central angle in radians. Never forget to use either of those formulas. That angle needs to be in radians. Now in our case it's not in radians, but we'll just take care of that right away. So we get 1/2 r squared, so 321 meters squared, times theta, which is 15 degrees. And if we turn that into radians right away, we need to multiply by pi over 180. So that's all there is to it. You just have to go ahead and now multiply it out. We'll go ahead and get an approximate answer for this. So we're gonna go ahead and multiply 321 squared by 15 times pi, and we're going to divide. Now if you're typing it out just like this, you have to be very careful, because if you write 2 times 180 right now, you'll get the wrong answer. So you'll want to use parentheses in a situation like this. You're going to write parentheses 2 times 180. An alternate thing to do would be to say divided by 2 and then divided by 180. That'll get the same job done. And we end up with approximately 13,488 to the nearest square meter. And don't forget, your final answer should always be presented with the proper units. So that's the area of the sector that is being irrigated. All right, so that should get you through the homework, and until the next lecture, have a nice day and be safe. I'll talk to you next time.